Hello everyone, you are welcome to my YouTube channel at GMAETS 41. In my previous video lesson on physics practical, I taught you how to carry out experiments on refraction of light through triangular prism. I went ahead to explain how you can quickly measure whatever angle has been required of you by your examiner in the exam or your lab technologist during your laboratory work. In this video lesson, I am going to present to you the table of values, the readings obtained for that experiment, and of course, the graphical interpretation of what we did in the experiment. You would recall that I told you that our interest would be on angle of incidence I, angle of deviation D, angle of emergence E. Now, using the given angle of incidence, we carried out the experiment for which I demonstrated you. You must have watched the video lesson, of course. If you've not done so, please, you can pause this, go watch that video lesson, find out how all angles are being measured, then you can continue with this lesson. I think that will help you more. But in that case, we have to continue in this video, right? Good. So, in the table of value, I evaluated D minus E, that is angle of deviation minus angle of emergence. Okay? Once again, let me show you the experiment. Just a reminder, you can see that. So something like this. In fact, this was the demonstration presented to you in that video lesson. Alright, at this point, I would like you to watch the screen, please, and you will see displayed the table of values obtained from this experiment. Using the angle of incidence 30 degrees, 40 degrees, 45 degrees, 50 degrees, 60 degrees, and 70 degrees. I obtained the angle of deviation D, the angle of emergence, and of course I evaluated D minus E. Please watch the screen as the table of values display. That is good. Now, using this table of value that was just displayed, I have plotted the graph of incidence angle I against D minus E. The angle of incidence was plotted on the vertical axis, and then the difference between the angle of deviation and the angle of emergence was plotted on the horizontal axis. I am going to display the graph now. In order to assist anyone out there that might have challenges on how to locate points in the graph, I've decided to show the processes I follow, right, of getting the graph drawn. Meanwhile, in this channel, I have a powerful video that explains fully how to quickly plot a graph. So I will encourage you to go through my general physics playlist, and of course you will see the video where I explain how to plot the graph. And so I'm going to display the graph. Okay, technically you will see the points showing, alright, the corresponding values of I and D minus E. And then of course you will see the line of best fit drawn, the scales selected. Okay, these are going to be displayed on the screen. So let us watch what the shape of the graph I against D minus E looks like. But I would like to state that this graph is a positive graph because the experimental theory guiding this particular experiment, for which I plotted I against D minus E, follows the equation I plus E, that is incidence angle plus emergence angle, equal to A plus D. Since I'm plotting I against D minus E, It means that I need to make I subject of the formula. And of course, making I subject to the formula, I have that I is equal to bracket D minus E close, then plus A. You can see the equation there. So if I'm plotting I against D minus E, the coefficient, the multiplier of this D minus E will become my slope. And of course, if you look at the D minus E in this equation where I made I subject of the formula, you notice that it is 1 that is multiplying the bracket D minus E. That is why clearly you are not seeing any number multiplying that bracket D minus E. It simply tells us that the slope is 1. The gradient of this graph is 1. And once again, this D minus E, just before the first opening bracket, the mathematical sign there is positive, not negative. Watch, I equal to, before opening the bracket, you notice that there is no minus. Therefore, it is plus. They have D minus E in bracket closed before the A. This simply tells us that the graph we are going to obtain I plotted against D minus E is going to be a positive graph. Okay? It's going to go this way. So please, take a look at the screen and you will see the graph displayed. Please watch. I will be explaining a lot based on what we have there. Remember, a plot of I on the vertical axis against D minus E on the horizontal axis. So you have your X and Y axis showing. The vertical axis is your incidence angle. The horizontal axis is your D minus E angle, the difference between the deviation angle and the emergent angle. Alright, so having chosen the scale, I'm going to trace the point I corresponding to D minus E values. So you can see the point appearing. Alright, there are 6 of them. Please, I did not just locate the point anyhow. From that table of values you saw, for a particular value of incidence angle, you have a particular value of D minus E. In fact, when the incidence angle was 30 degrees, D minus E was minus 30 degrees. So you see where it is located on the negative axis of the horizontal. Okay? Then in that order, when I was 40 degrees, D minus E was minus 20. So you can see the points being displayed. Okay, lastly, when I was 70 degrees, you notice that your D minus E was 10 degrees. So you can see it on the other side of the graph, the other end of your vertical axis. Look at when I was 60 degrees. So you can take a look at 60 degrees. You notice that the deviation angle minus emergent angle was 0 degrees. And therefore the point was found at that 60 degrees on the I-axis, that's the vertical axis. And then the line of best fit has been drawn, you can see that. Good. The line of best fit passed through the incident axis, that's the vertical axis. You can see that at 60 degrees. Then you can see it on the horizontal axis, that same line of best fit cuts the D minus E axis on the negative part, still at 60 degrees. So you have 60 on the vertical, 60 on the horizontal, which tells us that our graph, the line of best fits, actually has intercept on the incident axis, the vertical, and on the D minus E axis, the horizontal. Let us now move on, please. In the instruction here that I'm considering, we are required to state what the intercept on the vertical axis and on the horizontal axis represents. The intercept on the vertical axis and the horizontal axis simply represent the refracting angle of the triangular prism. The refracting angle of the triangular prism. How did I know that? Remember I told you in the plot, in the graph of incidence angle against D minus E, it follows the equation I equal to d minus a in bracket plus a. If you compare this equation with our equation of a straight line in slope-intercept form, you will have y equal to mx plus c. Now if we do the comparison, y is equal to the angle of incidence I, because we plotted the angle of incidence on the vertical axis. And then d minus e is on the horizontal axis, because that's what we plotted on the x-axis. So d minus e is our x-axis. In that equation of a straight line, y equal to mx plus c, m, the quantity multiplying what we plotted on x-axis, that m is the slope. So for this experiment, although we are not required to get the slope, however, if I were to evaluate the slope of this graph I plotted against d minus e, the slope will give me 1. Because slope n is multiplying the quantity you plotted on the x-axis. You can see it mx. Now if you compare it to the equation guiding our experiment, I equal to d minus e in bracket m plus a. What is multiplying d minus e, which we plotted on the x-axis, is a visible 1, as you are seeing in the equation. So automatically the slope of this graph, the slope will be equal to 1. Although we were not asked to find it because it's already 1 from the theoretical equation guiding the experiment. Now let us look at the last part of the equation of a straight line, which is c. Comparing it to the theory guiding this graph that was plotted I against d minus e, you see clearly that our c, which is representing intercept in the equation of a straight line, is equal to a. That a in that equation, I equal to d minus a in bracket m plus a. That a is called the refracting angle of the triangular prism. In fact, in the experiment, when I was teaching you how to measure your angles, I measured the angle, the refracting angle of the triangular prism I used, and it was 60 degrees. It was 60 degrees. So if the intercept of our graph is equal to a, and a is the refracting angle, it simply means that in answering the question, what does the intercept of both axes of this graph represent? As you draw this line of best fit, it cuts the vertical axis I at 60 degrees, cuts the horizontal axis d minus e at 60 degrees. Therefore, our intercept represents the refracting angle of our triangular prism, which I used to demonstrate the experiment. So take it. Intercept of both axes represent what? The refracting angle of the triangular prism A. That is that about our first graph, I plotted against d minus e. Now let us look at the second graph that we obtained from the table of values, okay? In the second graph, I plotted the angle of deviation against the angle of incidence. Alright? My aim in that plot is to obtain the minimum deviation of the triangular prism that I used for the experiment. When we talk about minimum deviation, well, there are certain information you need to get about minimum deviation. When refraction is occurring through a triangular prism, and you say that at this point there is going to be a minimum deviation, there are certain conditions that must be met. Well, let us quickly move to the graph, okay? Once again, I'm going to display the graph on the screen. You take a look at it. Like I said, I plotted a graph of angle of deviation D against angle of incidence. At what angle of incidence will I get the minimum deviation? Please watch the screen as the graph of D against I displays. Now you observe that this graph is a curve. Okay, it's a curve. So just like what we obtained in the table of values, okay, initially the angle of deviation started decreasing up to a point it started increasing again, and that is why this graph gave us a curve. You can see that. So, to obtain our minimum deviation, of course, the instruction that I'm using requires that we evaluate the minimum deviation from this graph. To get the minimum deviation, all you have to do is go to the lowest peak of the graph, where the curve turned, the lowest peak. You can see that. Now from that lowest peak, simply trace to the vertical axis. You can see the tracing there. The point where it touches it is our minimum deviation. We use dn to represent the minimum deviation. Now, following the instruction, we are asked to calculate the refractive index of the triangular prism that was used in the experiment, using the minimum deviation obtained from this graph, and of course the refracting angle of the prism. Well, before we talk about calculating the refractive index n, okay, using the data obtained from the two graphs, yes, the minimum deviation from this graph of d against I, and of course the refracting angle from the graph I against d minus e. However, for the refracting angle, okay, from your tracing, you may decide to measure the refracting angle. You can still use it, it's okay, alright, because normally it's expected that the refracting angle will agree with the intercept of our first graph, that graph of I against d minus e. Alright, so we are going to look at how to calculate the refractive index of the triangular prism. But before then, please, since you've known how we obtain the angle of minimum deviation from this graph, I would like to tell you the condition for minimum deviation to occur when light is passing through, is refracting through a triangular prism. At minimum deviation, the following conditions must be true. 1. The angle of incidence must be equal to the angle of emergence. That is to say, the angle at which the incidence ray met the outline AB. That angle of incidence must be equal to the angle of emergence. That is one condition for minimum deviation to occur through a triangular prism. 2. The angle of refraction at this face, this angle here, must be equal to the angle of incidence. You know, if the ray refracts through the prism, it is now assumed that the refracted ray will hit face AC of the prism. It will hit face AC of the what? Prism at this point. That refracted ray will hit that face and then come out. So that refracted ray that is meeting to hit face AC of the prism, because it is hitting that face AC and coming out, we refer to that refracted ray once it is going to hit face AC. We can refer to it as the incident ray at point AC. Then coming out, it will now refract through this emergent ray. So what am I saying in essence? The angle of refraction at this point of incidence along face AB is equal to this angle here. Look at this angle at point of emergence along face AC. And then finally, if these two angles must be equal, it simply means that the refracted ray will pass symmetrically symmetrically, that is to say, the refracted ray will be parallel to phase BC. It will be parallel because it will pass to divide this prism such that the line will be parallel to the base of the prism. So these are the three conditions at minimum deviation. Alright, the refractive index of the triangular prism. How do we evaluate it? Using the information obtained from our graphs. Now, the refractive index is equal to, it follows the formula, watch, sine, open brackets, A plus dn over 2, where the A is the refractive angle, the dn is the minimum deviation, that is angle of minimum deviation, all over sine A over 2, sine of the refracting angle over 2. Now, all we need is the value of the refracting angle A, which of course, from our experiment is 60 degrees. And our angle of minimum deviation, D, that dn, okay? Now, the angle of minimum deviation from this second graph, that is a curve, is equal to 37 degrees. Our refractive index n will now be equal to sine, open bracket, A is 60 degrees, so we have a 60 plus dn is 37 degrees over 2, divided by sine 60 over 2. Simplifying further, we have sine 97 over 2 will give us 48.5. So that's going to be sine 48.5 all over sine 30. Sine 48.5 is equal to 0.7489 all over sine 30 is equal to 0.5. Therefore, our refractive index, if you divide the 0.489 by 0.5, is going to give us 1.49 in 2 decimal places. If you approximate to 1 decimal, it's going to be 1.5, which is usually expected of a triangular prism. The refractive index is within that range. And so that is how you calculate the refractive index of the triangular prism. So for my own triangular prism I used that produced all this data which I have just analyzed graphically. The refractive index of my prism which I used in that experimental demonstration of refraction is 1.5 in 1 decimal. What are possible precautions taken to ensure accurate results in this experiment? First, you must ensure that the pins are placed on the incident ray. That is, pin 1 and pin 2 are neatly placed on the incident ray. Because if any of the pin moves away from the incident ray, are you following? It's going to cause you trouble. So you must ensure that pins 1 and 2 are neatly fixed on the incident ray before tracing. This is to avoid any possible interference. Are you following, right? When you are doing your tracing, because if pins 1 and 2 are not well fixed, to block them using pins 3 and 4, it's going to be a problem. There's going to be some form of interference. So that is one possible precaution. Then another precaution that can be taken is to avoid error due to parallax when taking your measurements. You know, when you are measuring all this angle of emergence, the angle of deviation, it is expected that you look directly down in order to be able to see exactly where the angle forms. If you look from the side, you may be committing error of parallax or error due to parallax. Another precaution that you can take while carrying out this experiment is to ensure that the triangular block or triangular prism is placed neatly on its original outline before you start blocking the image of pins 1 and 2. You know, when you are blocking the images in pins 3 and 4. If the triangular prism is not neatly and well placed on its original outline that you traced, if it's not placed back neatly on this outline, then it might be difficult for you to actually do your tracing accurately. Okay? So you want to ensure that the triangular prism is well placed neatly on its original outline. This also is to avoid possibility of interference of the rays of light. Alright, you can think of other possible precautions that can be taken to ensure accurate results in this experiment. I hope you enjoyed this video lesson. Please subscribe to the GMAETS 41's YouTube channel, like and share these video lessons. Leave a comment. If you have any question, please use the comment section of this video lesson, okay? Leave your questions there and I'll be right there to respond to your questions. In our next practical physics class, I'll be taking you through electricity experiment, verification of Ohm's law, to be specific. I hope to see you in my next video lesson on physics practicals. But remember, before then, other video lessons on other courses may appear. Alright? Remember here, there are a lot you can learn from GMAETS 41. So please subscribe to my channel, turn on the notification bell, so that anytime I upload a new content, you will be personally notified. Take care of yourself, alright?